Yeah, thank you very much for the introduction, and thanks to the organizers really for having us here in the beautiful scenic venue and with lots of delicious food. And of course, thanks to all of you for being with us here at the last session of the conference. So let's start. So here I am Subhradeep from Ludwig Maximilian University of Munich, and here I will be talking about bilayer Hubbard model that we see in a transition metal dechalcogenide heterostructure which forms moiré superlattice, as we will see here. So let's start. And I know that you are not seeing this slide for the first time today, but I will still show the motivation behind the material combination that we select in our study, which is these two materials with the arrows. So you can see that these are molybdenum diselenide and tungsten disulfide, and as you can see from the theoretical calculations, the conduction band offsets, the conduction band edges are really close in energy, and we of course have a large offset in the valence band. So we know that if we excite this system optically, all the holes will lie in the molybdenum diselenide valence band, but we have a very close band alignment in the conduction band for the two materials, and this can facilitate hybridization and interlayer tunneling of electrons. And yeah, this is one of the motivations to study the physical effects of this hybridization in our system. And another motivation is that we have two materials, the molybdenum and tungsten disulfide, which has a relatively large lattice mismatch. And we know that as we saw from the twist angle dependence of the moiré lattice, that if you bring in two lattice with two defined lattice constants, what you can have is as a function of twist angle, or because of the lattice mismatch, you can form like moiré superlattices, so which can extend to many lattice constants. And then if you have a large lattice mismatch, then you depend less on the twist angle. So then if the twist angle is relatively small, let's say 0 to 4 degrees, the lattice mismatch is the dominant factor, and you will have robust moiré excitons because of the lattice mismatch, and which will be relatively independent of the twist angle. And this was the main motivation of this study, because when you have the lattices to be almost equal, you can have large atomic reconstructions, as it has been shown in many works recently, that you can have 0D, 1D or 2D like excitons because of the intralayer strain in the lattices and the interlayer adhesion energy. And in a lattice of large mismatch, I mean, these reconstruction effects will be minimal, and we will be looking at the moiré physics only. So with these motivations, and also the fact that the precise band alignment, because they are so close, this precise band alignment was until now an open question, that some studies predicted it to be type 2, as in this study by the group of Alexei Tartakovsky, and we showed that we have a type 2 band alignment, namely the WS2 conduction band edge is lower than the molybdenum diselenide conduction edge. And there are other works which also showed that we should have a type 2 band alignment in this system. But recently there has been one work by the group of Kin-Fai Mark in Cornell, which showed that we have a type 1, such that the molybdenum diselenide conduction band is lower than the tungsten disulfide. And we want to study this system and see that what actually is the case in this system. And then we made this dual gate device, which also Anwar introduced in a talk in the morning, where we have this heterostructure, molybdenum and tungsten disulfide, and we have two gates, the top and bottom. And the advantage of such a field effect device is that we can tune the voltages of these two gates separately to have either electric field or doping, or a combination of both. I mean, if we had a single gate device, then we would definitely push charges in the heterostructure, but we would not be very sure that this is only doping, because in a single gated heterostructure there is unavoidable effects of electric field as well. But in a dual gated structure, if we make sure that we have antisymmetric voltages, that the sign of the voltages applied to the top gate and the bottom gate is different, then we are always in the neutral regime and looking at only electric field dependence. And if we have symmetric gate voltages, then you see that if we have, let's say, 10 volts here and 10 volts here, then we don't have any mismatch of volts in the top and bottom gate layer, and then there is no out of the plane electric field, and then we can study the doping only. So because of this advantage of a dual gate structure, we make this device in order to study, let's say, doping or electric field or a combination of both. And then what we have because of the moiré potential is that we would have Umklapp scattering from the long range moiré superlattice, and then we will have 3 peaks in the molybdenum only, that we have this type 1 band alignment, at least in the neutral regime, without any effect of electric field, and then we will have 3 moiré peaks experimentally observed, and all of them are from the molybdenum diselenide material. And this is the data in absorption and photoluminescence. In absorption, we see these 3 peaks, and in photoluminescence, we have a quick population relaxation and have only the lowest energy moiré peak, which we call to be M1, M2, and M3. And now we will study its doping dependence and electric field dependence and try to understand the specific origins of this. If you remember Anvar's talk, he showed you how these peaks behave as a function of electric field, and by narrow band differential reflectance measurements and theoretical calculations, we were able to show that we in the neutral regime without out of the plane electric field, we have a type 1 band alignment, but as a function of electric field, the tungsten disulfide conduction band can be pushed lower to the moly diselenide conduction band, and we can have a type 2 band alignment where the interlayer exciton would be the dominant recombination instead of the intralayer exciton, as is the case for the neutral regime. And here I will look at more closely at the doping dependence. So here we have 0 electric field, so that symmetric sweep of the gates, the same voltage is applied to the top and bottom gates, and this is what we observe. I mean, this is the neutral regime at 0 volt, let's say, where this is the intrinsic regime and this is the n doped regime, and here we have the p doped regime. And as you can see in the neutral regime, we have 3 moiré peaks, the M1, M2, and M3. But what is more interesting is what happens as a function of doping. We see in the p doped regime the behavior is less rich, that we have this M1 plus trion, and here they lose oscillator strength, the M2 and M3. But in the n doped regime, we have as soon as it moves into the n doped regime, we have these trions M1 minus and M2 minus tilde. Like from their energies, we can say that they originate from different physical effects, because there is a large energy mismatch between the M1 and M1 minus, which is about 30 milli-electron volts. So this is a typical energy difference between a neutral exciton and a charged trion peak, which means that the electron is co-localized with this M1 exciton, and this is very strongly bound. And this is why we have a energy difference of 30 MeV. So this is the binding energy of the trion. But the scenario is not the same for M2 minus tilde, where we see that the energy of the M2 minus tilde is not so different from the neutral M2. So this means that there is definitely another charge that is attached to the M2 exciton, but then it is not exactly where the M2 exciton is present, but it is remotely bound. So this is why the binding energy is so small. And this has many implications which will be clear in the coming minutes. And so what we see here is that in the n doped regime, we first have these 2 peaks, and then we lose oscillator strength of the M1 peak as a second charging step. And what we have is that M2 minus and M3 minus peaks in the second charging steps. And by the way, here we recovered the bound trion so as to the high binding energy trions in the second charging steps. So yes, and then of course, like we have this high symmetry points in the moiré superlattice, and we can show by modeling the superlattice potential and from the energies that these M1, M2 and M3 excitons originate from different spaces in the moiré lattice, as Anvar has also showed. And this XX site where where two chalcogen atoms are immediately close together, there we have the M1 excitons, and from this MM site where one metal is on top of another metal, we have this M2 exciton. And then if we look at the DR spectra at in the endoprism here, we would see these two excitons, and if we take a derivative, we have a large contrast of it. And then since this is a remote trion, that is one electron is loosely bound to the M2 exciton, this we will study as to understand what happens in the lattice in proximity, because this is loosely bound, so it is sensitive to the physical environment around it, and it will shed more light on what happens to the MOSE2 lattice as we feel more electrons on it, and what happens to the WS2 lattice as well. So now I mean this is hyperspectral data, so I have to spend some time here to explain. So this is a dual gate map of the absorption response, so from the differential reflectance and the derivative of it. But I mean here what we can see here is that each point represents a spectra, right? So each point is the maximum of the spectra in the range 1.6 to 1.8 electron volts, which is the main range of our optical signal. And then if we take line cuts around, let us say a line cut here, it will represent doping dependence of the spectra, and if we do it exactly in the center, it will be in the neutral regime, but if we do it above or below, it will be a combination of doping and electric field. And this is how we can try to understand the hyperspectral data. And we can see that there are three different regimes that we can observe in the n-doped regime. So if this is the zero line, so on the right hand side we have the n-doped regime, and in this work we will focus only on the m-doped side. And so one color here would represent that the optical signal is more or less identical. And if we have a transition from one type of spectra to the other, it will mean a difference in the optical signal as well. So let's see what this means. So now I will take three line cuts here. So and then here, as I just explained, that A2 will be the line cut where we have zero electric field, and here we have finite electric fields for the A1 and A3. So let us try to understand what we are seeing in these line cuts. So A2 is where we have zero electric field in here, so that this line is the symmetric sweep of the top and bottom gates, and here is what we see. So this I also showed you before, is that first we have the M1 exciton, and then when we have one electron per moiré cell, which is the filling factor 1, we lose this neutral exciton and we have the M1 minus and M2 minus tilde, and then we have a second charging step, as I just explained you before. And then if we have a negative out of the plane electric field, that is the electric field is pointing, let's say, from the MOSE2 to the WS2, we can see that the charging step here happens at earlier gate voltages. And you could understand it as follows, that when you have this finite electric field here, what we have is that we increase the conduction band offset of the moly layer and the tungsten layer. And then all the charges that we are trying to put in the system are being put in the molybdenum layer, and then we have this charging step to happen at smaller gate voltages. And the opposite thing happens when we have a positive gate voltage, that here in this case we have a type 2 band alignment to begin with, and now the tungsten conduction band is lower than the moly conduction band, so the first electrons are put in the tungsten layer. I mean, I am saying this because I know that all the moiré excitons arise from the moly layer only. So this is why between the filling factor 0 to 1 we see very little change here, because now the electrons are put in the tungsten layer. We see a small redshift here. I am not sure if it is visible in this data, but we see this small redshift just because the electrons are being put in the tungsten layer, and it kind of senses it that the local environment is changing, and this redshift is reminiscent of that. And then when we put more and more electrons in the system, finally the moly layer starts to be occupied, and then we have this M2 exciton and then the trions finally. So then these spectra all represent like the doping behavior with or without an electric field. And then it is also another nice confirmation that we definitely have like type 1 band alignments here and type 2 here. And then we can also say that what is the band offset, what is the conduction band offset between the moly layer and the tungsten layer, because we see that this happens at a particular electric field, and from the value of the electric field we can also deduce that what was the band offset of the moly layer and the tungsten layer to begin with, and this is about 30 milli-electron volts in our system. And now with this intuition, we wanted to model this hyperspectral data by an electrostatic model. So let's say we consider density of states where the density of states of moly diselenide is higher because they are situated at a strongly confined superlattice potential in the moiré lattice, and then at this 30 milli-electron volt offset we have the density of states of the tungsten as well, and then we take into account the geometric capacitance and the quantum capacitance of the system in order to find out what will be the final electron density in the molybdenum diselenide layer. And this is what we want to calculate here as normalized by the moiré density, which is 2 times 10 to the 12 per centimeter squared. So we are trying to plot the MoSe2 electron density here, because what we essentially see here is from MoSe2, right? So there is nothing from WS2 here. So we are trying to see that because of our electrostatic model, if we can reproduce the data set that we have here. So then as a first step, I say that okay, the density of states of moly diselenide is here, and here I have the tungsten, and then the final density will look like this. And you see that we starting to have one step here, but not all of them. So we have to say that the density of states will not look like this, but a bit different. And then this is the only fitting parameter in our calculations, and the rest is defined by the geometric capacitance and the capacitance of the system. And then we say that we have this at this 30 milli-electron volt band offset, we have a density of states of the lowest density of states of the tungsten, and then above a certain energy U0 we have again the density of states of tungsten. So that means the density of states is discretized because of the superlattice potential, and this U0 is just the Coulomb gap. So that means that if one electron is already there, what will be the cost to put another electron on the system, and this gap is defined by U0. And then if we repeat this argument and say that the same thing happens in the molybdenum diselenide layer well, that there also the density of states is discretized, we can recover the steps that we observe experimentally. So then here is the Coulomb gap in the moly level, which is U1, and then finally it's with this kind of density of states that we have this moly layer, and at a certain conduction band offset tungsten layer, and then again the Coulomb offsetted moly layer and tungsten layer. We can say that then the density of states are discretized and proceed as follows, that first we have a charging of the moly layer, and then we charge the tungsten layer where the moly layer is kept at a constant filling, and then only when the tungsten reaches this filling, then the moly layer can be populated again with further electrons, and at that point the tungsten layer will remain constant. So we have a layer by layer charging in our system, so that when we try to put electrons in the system or we try to dope the system, the first few electrons will go to the molybdenum diselenide layer until we reach 1 electron per moiré lattice, and then we then fill out the tungsten layer and so on. And in this picture we can, as you can see, that we can reproduce most of the behavior that we can see. So this was a very interesting result for us, that we could finally understand the hyperspectral data and had a very good intuitive understanding of how the charging occurs in the system. just to summarize, what we have here is that first we have an exciton at 0 filling. So that you see that these are the filling of the moiré cells. So red is the molybdenum layer and the blue is the tungsten layer. And then from filling factors 0 to 1, we fill up the molybdenum layer, and then between 1 to 2, we fill up the tungsten layer as signified by the blue dots. And we know one more thing here. We know that these two lattices are not only vertically displaced, but they are also laterally staggered, because if you looked at the data here between filling factor 1 to 2, when the tungsten lattice is filled up, there is minute change in the spectra from these excitons which are in MOSE2. So that means that the electron filling in the tungsten cannot occur in very close proximity with the moly layer. So they are also laterally staggered. And this can be verified in certain ways, which I will show now. But now we have a more or less intuitive picture of how the charging happens in the system. And now we want to see that whether this special type of charging leads to some spin correlations in the system or not. And to study spin correlations, we want to know the magnetic susceptibility of the system, because if the magnetic susceptibility increases or tends to diverge, that means that we have more spin correlations, or the spins in the system are correlated. But before studying that, we would also show the trion binding energy of this M2 exciton, which would be important to study the spin correlations as well, where we try to calculate the binding energy of this M2 minus tilde trion. I mean, from experiment we have this data, which is the blue, the red and blue data, where up to from filling 0 to 1 we have the molybdenum filling, and from 1 to 2 we have the tungsten disulfide filling. And then we also wanted to calculate it by trying to see that what the binding energy of the system will be when we consider the electron and hole relative motion in the system in this moiré potential. And our calculation matches more or less well with the experiment, and this calculation takes into account that we have this laterally staggered lattice as well. So we just here try to populate the two lattices and calculate the binding energy with our understanding from the previous layer by layer charging and the laterally staggered model. And we find a good agreement that says that, okay, so our understanding is consistent with the binding energy of this trion as well. And now we move on to the spin susceptibility of the system, and here we can measure the susceptibility in two ways. One is the magnetic circular dichroism, which looks at the optical contrast when you collect from sigma plus polarization and sigma minus polarization, and another is the exciton Lambda G factor, which is the Zeeman shift of the excitons, which takes into account the fact that if you collect the sigma plus polarized light and the sigma minus polarized light at a certain non-zero magnetic field, then their degeneracy is broken and you have a certain shift about in the sigma plus and sigma minus light because of the exciton Zeeman effect. And then you could fit that data, the energy shift, and then find the G factor, and that will then be proportional to the magnetic susceptibility in the system. So here we will mostly focus on the G factor studies, where we have this lattice of MOSE2 and WS2, and then you see that how the shift behaves as a function of magnetic field. We can see that it is highly nonlinear, that at a very small magnetic field we have a large shift, and then at high magnetic field it tends to recover this value or even saturates. By the way, this saturation value is what one can expect from a monolayer exciton, which is like a -4 G factor. But we see that how it becomes highly nonlinear here in this case. And this is also a function of temperature, as you see that at high temperatures, which is like at 16 Kelvin, it is mostly the monolayer behavior. But as we lower the temperature, at the lowest temperature of 160 millikelvin, we have a highly nonlinear effect. And then from here we could do some more analysis of it, that we see the G factor as a function of temperature, which shows this kind of behavior, which is also quite typical Curie-Weiss behavior. And then we wanted to also plot the shift as a function of magnetic field normalized by the temperature to see that all the curves basically collapse on top of one another. So that all the behavior that we see are a function of thermal excitation in the system only. And then here we do the G factor studies as a function of filling. So between 0.5 and 1 we have filling. So this is the filling factor. So here we populate the molybdenum lattice, and here we populate the tungsten lattice. We can see that how it increases to a certain value of 600, which is in case of TMD excitons quite large, and then it shows some oscillations and variations of 10 to 15% up to the filling factor of 2 and beyond. And here we have to stop because we calculate the we see or measure the G factors of M2 minus tilde only, and above this filling factor it disappears. So we have to stop around here. And then from the Curie-Weiss law we could extract the Curie temperature of the system, and where we see that this is more or less negative values, and we show some fluctuations here, and the negative values would mean antiferromagnetic correlations of the system. And now, I mean, this is a very rich set of data, and we did not want to feel very stupid, let's say, and wanted to understand what really happens magnetically. And then we reached out to some theorists in our institute in LMU, and they invoked the classical spin Heisenberg model in order to calculate the spin susceptibility difference between filling factor 1 and filling factor 2. And the spin susceptibility difference theoretically, they calculated it using the Markov chain Monte Carlo simulation, and they saw that how the difference of the spin susceptibility can reduce when you invoke the interband coupling, interband magnetic coupling. And we also observed something similar in our experiments as well. So this is at least in the consistent direction, and where we can see that how the interlayer coupling can reduce to magnetic frustrations, and that can reduce the correlations in the system. And then we could take this interlayer coupling, that we have this kind of system where at filling factor 1 we have a rigid lattice of electrons in the molybdenum, where there are in every moiré cell there is 1 electron present, and between filling factor 1 and 2 we are trying to populate the tungsten layer, and then we put one or more electrons or more and more electrons in the tungsten layer, and then in the tungsten layer we have a Fermi liquid or a metallic layer, and these electrons in the metallic layer can interact with the spins in that is already situated in the tungsten layer, and can give rise to enhanced frustrations in the system, so that the spins in the molybdenum layer can cant and move and point to out of the plane direction that can reduce their correlations. And then we see that if we have like spin contributions like the J2 RKKY, which is like the spin the spin interaction between here, and also the long range spin contributions, and their effects were calculated, and it was seen that if they are positive or negative, they can contribute differently to the 120-degree antiferromagnetic order or not. So depending on how they vary between filling factor 1 and 2, we reached regimes of antiferromagnetic and ferromagnetic regions. And indeed, as predicted by the theory, in the antiferromagnetic regions we have a lower spin temperature. So that means we have a antiferromagnetic order, and then we break this order in the gray shaded ferromagnetic regimes, for example. And then we had this kind of understanding, at least here. And then we had some speculations on why this shoulder is seen here, and then what also signifies at filling factor above 2. But this we speculate to be a result of kinetic magnetism. And in the kinetic magnetism, what we have is that we have more electrons in the system, and they tend to kinetically align their spins in order to reduce the total energy. And this is just a speculation, but we need more understanding or maybe more calculations on it. And so this is where we stand until now in the system, and I will just quickly summarize what we observed. So we could observe a staggered bilayer triangular lattice exhibiting Hubbard model physics, and then we have the charging in the system to be layer by layer, that first one layer fills up and then the layer is being populated and then it goes on. And now we know what is the conduction band offset in the system and if it is type 1 or type 2. And then we have spin correlations in a vertically offset bilayer lattice, and we can tune the RKKY interaction in the weak antiferromagnetic regime, and also it can be tuned as a function of doping in the system. And then I will just finish by acknowledging all the people that were responsible in this project. So this is our group in LMU Munich, and in the experimental group we have Borislav, Johannes, Anvar and Alex, our advisor here. And then we received theoretical help for the magnetic calculations from Fabian Gruz, Tanabel and Henning in the same university. And I would thank the funding agencies ERC and Alexander von Humboldt Foundation for support. And with that, I thank you for your attention and will be happy to take any questions.